Sir, are you showing the screen?
No, not yet. Just a minute. Yeah, okay. Fine. So, as I can see, you guys are doing the quiz preparation. So, very less of you have joined. Anyway, I have to complete week 5 discussions. But before that, if you guys have, there would be a separate revision session on Friday. Atul sir would take that. So any other than that, any that in that revision session, all the topics would be discussed in detail for your examination. But still, before moving to week 5 content, uh, any specific portion up to week 1 to 4 where you have doubt? Not one is Python. After that, 2, 3, 4, where you feel there is a difficulty. I would not discuss everything. If you have any specific topic, then maybe I can discuss that a little bit and then move on to week 5 content. Anyway, week 5 wouldn't be complete today. And I don't want to do it completely on this day because many of you are not here. So if you have any specific topics, you can tell. And a detailed revision session would anyway be there on Friday. No specific doubts? Okay, fine. No problem then. But I think in this course, someone wrote that you guys are feeling a little bit difficulty in analyzing recurrence relation, the complexity of recurrence relations or recursive codes. I mean, so I would slightly touch upon that.
Okay, sir.
We have anyway discussed how to analyze recursion codes once, and it is quite easy actually. So I would request whoever felt difficulty in that to visit that. I don't know which session it was. So I think in week 2,
So
week
week 2,
2,
session 2.
yeah, thanks for that. So week 2, session 2, or yeah, just check those the initial week 1, week 2 sessions where we have discussed all of that. What is recursion, what is call stack, and all of that. If you want a background, and if you just want to see how to analyze the time complexity, then week 2, session 2 you can refer to. And still, I'm repeating a little bit over here. And the thing is, so let's say you have a function, anything, any naming function with some arguments over here, and this is a pseudocode. Okay. So, anyways, then first of all, here you would have a base case, right? Any recursion code must have a base case or the terminating case. Terminating case, right? And after that, we would have some task that we would be doing in these lines. And if the base case is not getting true, right, that means it is not the base case, then in that iteration, we would execute some task over here, some random task. And then at the end over here, we would have the recursive call. So this is the general structure of a recursion function, recursive function. And how to analyze the time complexity of a recursive function is by using recurrence relation. So how can we analyze to analyze complexity? Of recursive function, use recurrence relations. So what do we mean by that? So basically, we would write the time taken by your function fn when the input size is n, right? Can you all see my cursor today? Is it moving?
Yes, sir.
Cursor is visible, or is it only visible when I'm writing, or is it now also it is visible?
No, it is not visible, sir.
It's not visible.
No, sir.
Is it visible now?
No, sir.
Fine. Okay, so what I mean is you can use a TN. TN means the time taken by the function to work upon it when the input size is n. And I can express it in the form of some task that is done, this random task, right? So let's say the random task which is done over here takes order n squared time, right? So let's say there are two for loops, I mean, which is running till n. So that would take n square amount of time. So I would write it as order of n square plus whatever is the recursive call. So let's say the recursive call is fn of n minus 1 plus fn of n minus 2, which you might have seen in the Fibonacci call, right? Fibonacci sequence. So I would write it as t of n minus 1 plus t of n minus 2, right? So this is basically the structure of our recursive recurrence relation formulation. So if I change this to something else, so let's say if I change this to merge sort, then how would it look like? What was the, how did we write the merge sort code? It was something like, let's say your merge sort, some parameters, all the parameters are over here. And then inside it, what do you write? If beginning is less than equal to end, then you calculate the middle. Right, you pass the array on which you are working. So let's say or whatever it is. And with that you pass the starting, beginning, then you pass mid, and let's say then you pass size, or you might not need size, depends on your implementation, merge sort. And finally the merge. Right, something like this is the code of merge sort. And if I go to the complexity, what is the complexity of merge? It is order of n. And these two are recursive code, right? Because these two are recursive code, and basically this is your base case. If beginning is less, sorry, if beginning is less than equal to n, the opposite of that, that is the else, is the base case where it would terminate, right? So if we would have one else over here, no need to write that, because anyway we would not do any task, it would just terminate. So I'm not writing it, but else is basically the base case, right? Which we need not write. So fine. So how would this?
Sir, why we use this merge function?
Sorry.
Why we use this merge function?
A merge function we have discussed in merge sort, right? That merge function.
No. We separately defined merge sort for starting and the end. I mean, like the distribution what you had done for the middle.
Sorry. Yeah, I am parting it to merge sort here. This is the recursive part. And
Yes.
merge function would actually pick the elements one by one, that comparison, right, that we discussed.
Okay, after merge sorting the array, after merge sorting the array, then we have to merge it, right?
Yeah, yeah.
Okay.
So none of merge sort. This is basically the code of your merge sort, and the merge function I'm not writing because I want to discuss the recurrence part of it.
Okay. That's right. Okay.
Okay, I'm just trying to discuss the recurrence, some example of recursive codes. So merge sort is a recursive code, quick sort is a recursive code, because here I am calling the recursive call, right, of merge sort. So, okay, so let's see, this is a practical example of a recursive code, which we anyway have learned the algorithm for. So what would be the recurrence for this? Same thing, T of n. So initially when the array size is n, so what could be the time complexity? First of all, this task is taking order n time, right? So this is that. So if we go to our template of recursive codes, we would have a base case, right? So this base case is basically the else part that I just discussed. After that, we would have some random task. So over here, what is the task? It is order n task, which is over here, the merge function. So your order n plus the recursive call, right? So the recursive calls are these two. So this is also a random task, by the way, which is order of 1, but that doesn't matter because anyway, that's a constant type. So you would not consider that. Even if you consider, it would get neglected. So no need to write that. And merge sort is after that. So 2 times we are calling merge sort, right? 2 times we are calling merge sort. So 2, and then we would write T of. Now, how much amount of array are we again passing over here? So we saw that given in this example, we wrote n minus 1, n minus 2. That's why here I wrote n minus 1, n minus 2. So here I'm passing from beginning to middle. And in the next call, we are passing middle to end. So basically, we are dividing the array into 2 halves. So this iteration of merge sort, the size of the array was n. Whereas in this iteration of merge sort, the size would be half from middle to beginning to middle. That is n by 2. Accordingly, here also it would be n by 2, right? So basically, I'm passing n by 2 in the next one. And how many times merge sort is being called? 2 times, right? 1 time, 2 times. So 2t n by 2 plus order of n is basically the recurrence relation for merge sort. Okay, and like this is a random example. This is the recurrence relation for this code, provided that we are calling this function f of n minus 1 plus f of n minus 2. Right, so simple. This is how we form the recurrence. And now once the recurrence is formed, all you have to do is back substitution and calculate. So like in this example, if we solve it, whenever you remove order, right? Whenever you are removing order, so it is always advised to put a constant and then put n, right? So whatever. So let's say you are removing order of n square over here. So like this. The next line here, you should write c into n square. Doesn't matter. I mean, at the end of the day, that constant would anyway be moved out. But when you are solving on your own, right? But in our exam, it would be MCQ. So it doesn't matter whether you solve it on your paper with C and if you do not do. But in a subjective exam, if you write, if you directly replace order of n square with like this, then it would be a wrong statement to me. So good practice is always put a constant, because order means you are asymptotically removing the constant when you wrote order n square. So when you are again doing the reverse mapping, it's always advised to put C. So anyway, C of n square plus T of n minus 1 plus T of n minus 2, like there in this case we are writing C of n plus 2t n by 2. Now let's do the back substitution. So once I do back substitution, what is the meaning of T of n by 2? So T of n by 2, let's say this is 1. T of n by 2, if I substitute this, right? So this is T of n. So basically, I'm removing n by 2 at all the places. So what it would look like is T of n by 2 equal to C of n by 2 plus what? 2T of n by 2 by 2. Right. Right. Something like this it would look like. Once it is done, this is what? C of n by 2 plus 2T n by 2 square. So this is T of n by 2. Now what do we do? Put this T of n by 2 in our original expression in this place. So this is what back substitution looks like. So in that case, T of n would become C of n plus 2 into this whole thing, right? So what if I reassemble it, then what it should look like? 2 square into t of n by 2 square plus C of n plus C of n. Fine. So this is what T of n looks like now. Accordingly, if I do this for, let's say, some k steps, fine. So after some k steps, it would become 2 to the power what? K, because here 2 is there, here also 2 is there, here also 2 is there. So 2 times I did that and I got 2 2s. So here let's say k T of n by 2 to the power k plus C of n plus C of n plus dot 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 plus C of n. Now how many times will I get this? Because here I had 2 times, here also power was 2, so basically here I would get k times. Fine. Just mapping that. And now how many times I can do this, right? The next question is, so every time I'm halving it, right? So how many times can I do this halving? So that I told you that if I have an array of length n and every time I'm halving it, so let's say I can do this halving k times. So I'm k times halving the array. So till what? How many times can I do that? Till the array is reducing to a single element, right? Because you cannot break a single element. So till it's getting reduced to a single element. So now that is n equal to 2 to the power k. Solve it. Just log n base 2 is equal to k log 2 base 2, which is 1, or k equal to log n. Right? So we got k equal to log n. So now put that 2 to the power log n base 2 t. What is this 1? N by 2 to the power k is 1. So 1 plus, how many times we did Cn into k, right? So Cn into k. So this k would become log n. Cn into log n. Now, this by property of log, you know, I can write it as n. Yeah, someone wants to say something? Fine. So this is log to 1. That is n plus Cn log n. Now, if I consider the asymptotic term, then it would be the highest order, which is n log n1, because n is lesser, so n log. So that's just it. Once you frame the recurrence relation, all you have to do is back substitute. Yeah.
In the second last line, sir, how would the 2 the n? So I
Second
couldn't
last line?
follow, sir.
This one?
Yes, this line. Yes, sir. Yes, sir. Means in the before this line, it was 2 to the power log 2n. Now
Is this
in
line
the
clear?
it has
Till this
become
line, is it clear?
Yes, sir.
Okay. K we got
Till this
log
line,
n. Yeah.
Yes,
So
sir.
K we got log n. We just substitute in this line. So that's why we got this line. Okay. Now after this, what we are doing is only
Sir,
this.
hello, sir.
Yeah.
Sir, can you explain this once more? Actually, I was not able to listen completely your explanation.
Okay. Okay. I will explain.
Short.
Just a minute.
Yeah,
Yeah.
please. Sir.
So. Okay, let me just tell this first once, then I would again re-explain. So how we are moving from this line to this line, it is that only one thing we are doing. Here I have 2 to the power log n base 2, right? This is what we have over here. And I'm telling you
Yes.
this is equal to n to the power log 2 base 2. So this is a property of logarithm. If I generalize it, wait.
Okay. Got it, sir.
Got it?
Yes, sir. You got it, sir. Got it. Sir. Thank you so much, sir.
Yeah. So this would be equal to c to the power. Right. So this is the property of logarithm by which we are doing this step.
Yeah. Now it's
Yes,
clear. Thank you so much, sir.
Yeah. Okay, now let us discuss the whole thing again once. Fine. So what are we doing is, at first we are framing any recurrence code. If you have a recursive code, if you want to frame the recurrence relation for that and find the time complexity for that, all you have to do is frame this recursive equation, recurrence relation. So we are framing here T of n equal to order of n, right? So basically there would be two parts in a recursive code. First would be a recursive part, and then would be the normal, some task, some definite task that we are doing. That is the non-recursive part. So in this code, in merge sort example, which is the non-recursive part, this one, merge algorithm, because it would be the recurrence would be with respect to the merge sort function. So these two are basically the recurrence call. So basically this is your recursive part, right? And this one code is this one line is basically the normal sum task, inner task that you are doing in the function, inner task. Fine. So both any recurrence relation would be made up of two parts. The first part would be the task that you are doing inside that function, and the second part would be the part corresponding to the recurrence call, recursive call. So in this example, recursive call we are doing twice. Merge sort is being called twice. This is the same function, merge sort. So that's why we are using two times we are calling. And then we would be seeing that how much amount of data you are passing in that recursive call. So initially here the first call of merge sort was with array size n, right? The full array. But in these two calls, we are only passing from beginning to middle in the first call and the middle to end in the second call. So that means we are basically halving the size of the array and passing it in the subsequent iteration, right? So that's why in the parameter here we wrote n by 2 because we are passing half of the array. If you go at the top, here we were passing n minus 1 and n minus 2, and initially it was n, right? Here we are passing with n minus 1 and n minus 2, therefore here tn minus 1, tn minus 2 was there. So whatever is the reduction in your parameter size, you have to write that. It can be n minus 3, it can be n by 3. Yeah.
In the above example, you wrote order of n square. How it came from, sir?
This I mentioned it over here. No? Order of n square is the task. Suppose this is the task that this random task over here.
Okay.
So just assume there are two loops.
Mhm.
Right? For
And sir, whenever there is a nested loop, we try to we try to multiply the complexity of each for loop. I mean,
yeah, obviously.
Yeah.
Yeah. So nested loop means what? So basically, when you're writing the asymptotic complexity for in a nested loop, so every iteration of the outer loop corresponds to an iteration of the inner loop. So like in this example, where did it go? So like in this example, for I in range n and for j in range n. So what does that mean? For when I is 0, j would be going from 0 to n minus 1. When I is 2, j again would be going from 0 to n minus 1. When I is 3, j again would be going from 0 to n minus 1. So what does that mean? J is going from 0 to n minus 1 for every value of I, and I is ranging itself from 0 to n minus 1. So totally, how many times it is iterating? I is iterating for 0 to n minus 1. And for every I, j is iterating from 0 to n minus 1. So that means for I, we are having, so total number of iteration, if we calculate, that would be what? Multiplication, right? So n minus 1, sorry, not n minus 1, n minus 1 means n iteration. So n iteration corresponding to I multiplied by n iteration for each of I, which is j. So basically n square. Right? So nested loop iteration is n square. But again, you have to worry about that. How is the function is growing? So here for I in range n and j in range n, this is in this manner. That's why we said it like that. So I would discuss for example more, and if you can revisit the previous session, there I discussed multiple cases where log is coming, where exponential can come, all those examples, right? In the initial week 2 sessions. So fine.
Right.
Anyways, let's come back over here. So here order n 2tn by 2 is this, and order n is the inert task that we are talking about. Inert task is this one, which is the merge, and merge algorithm. We know that it takes order n time. So this is my basically recurrence relation. After that you have to just back substitute it and solve it. Back substitute means what? Here you are doing n by 2, right? So whatever parameter you are passing, just apply that. So let's say here it would have been n by 3, right? Suppose this would have been n by 3. So your next substitution would be t of n by 3, right? So whatever is the substitution over here, just apply that. So here it is 2 now. Let's do that now. 2tn by 2. So what would be tn by 2? Tn by 2 will be in terms of t of n, right? T in terms of t of n. If I just put t of n by 2, how would it look? It would be looking. I just substitute n with n by 2. So just apply this in this equation. C of n by 2, C of n plus 2tn by 2. Substitute n equal to n by 2 in this one equation. So C of n by 2 and then 2tn by 2 by 2. So this is this one, like that. So after that I'm rearranging and I got this term. Right. Now if I
So,
do
sir,
this,
whenever
yeah,
we are backtracking, we are putting n by 2 in the first
not n by 2.
line.
Whatever is there
I
in
mean,
the
yeah,
argument.
I'm
Yeah.
concerning to this example. We are
Yeah.
saying that when you are trying to add a n by 2, sorry, it substitute n by 2. So each time it is instead of n, it is coming n by 2 once, and then suppose if you are going again with n by 2, so it's getting multiplied, right?
Yeah.
N by 2
Yeah.
square and like that.
Exactly. N by 2, then n by 2 square, n by 2 cube, like that. It would go on.
Okay.
So that's why generally after k steps, it would be n by 2 to the power k. Right? Like this.
Okay.
This line.
Hmm.
If you apply
But
k, yeah.
so this last step Cn, it's coming k times. How, sir? Because we are adding n by 2, right? I mean, substituting n by 2.
Yeah, just solve it now. Just see how this is coming. So C of t, this, let's see this line. This line you see. T of
Yeah.
n by 2 equal to Cn by 2 plus 2tn by 2 by 2. So basically this is the term C of n by 2 plus 2tn by 2 square. So this is what? Tn by 2.
Yeah.
Now I am putting Tn by 2 in this equation. That's why I have written this arrow. Just put this Tn by 2, whatever you got, in our original expression. This is where we are doing the back substitution. We are back. I mean, I'm coming back to our previous equation 1, substituting the value of Tn by 2 that I found over here by this new value. This new value is this value basically, right? So if I substitute this whole value over here,
Okay.
right? So then I'm getting this T of n is now modified as this C of n was there, this C of n is there. Here 2 was here, 2 is here, and then I have Tn by 2. I will place this in place of the Tn by 2. So that is this thing. See, these two are
Okay.
same. Right? And after that,
And
you just solve it, you get this term.
so after this, we have to take 2 inside the bracket and
Yeah, normal solution.
a
Simplified.
normal solution, simplification.
So basically, I applied this two. I mean, I'm doing it 2 steps. So n by 2 I did, and by doing it by till n by 2 step, I got 2 times C of n. If
Yeah.
I repeat
Yeah.
once more, so let us, for the practice, let us repeat once more. You would understand.
Yes.
So if we do this, So from where I'm repeating from here.
Yeah.
So what is my code? T of n is equal to 2 square t by 2 square plus c of n plus c of n. So this is how my code looks. Now I would again do reapply back substitution. Okay, so what would I do again? Put t of n by 2. You already know it is equal to what? C of n by 2 plus 2t n by 2 square. Right? So how did we get this term? We simply replaced in our original equation. In our original equation, we simply replaced n by n by 2. Right? Replace wherever you are getting n by n by 2.
N by 2.
Okay. So that's our main part. So that's how we got here. So okay. So here we got t of n by 2. If I again reapply this, how would it look like? 2 square. That is fine. Right. After that, Tn by 2. So exactly. So what is this, by the way? N by 2 square is there.
N by
Right?
2 cube.
Yeah. So this would become okay. So do it step by step. So 2 square I have, that is fine. Now here I have t of n by 2 square. Now what should I write in place of that? Any idea?
Instead of n, we can write n by 2 in place of n by 2 square, n by 2. So n by 2 cube.
Okay. So
I'm replacing n by 2.
that is fine. Okay. So t n by 2
2 cube.
cube. After that,
Plus c.
no.
C n
See,
by
one important part is that's what I'm saying. When we are going for back substitution, this is t of n by 2. That is fine. But what is the after the first level? So let me state it in this manner. Otherwise, it is getting confusing. So what I mean is, so initially the expression was what? Wait, let me delete all this. Initially, the expression was this: c of n tn by 2, and now I have to do substitution on it. Now, in order to do back substitution, what is the term that I'm thinking of? This is the term that I'm trying to substitute. N by 2. T of n by 2.
T of n by
This
2.
one. Yeah, this one, right? This one is the one where I'm doing the substitution. Here T of n by 2 was there. So T of n by 2, I found this value and I substituted this value over here.
Okay.
Right? So in this is the primary equation. This is my primary equation.
T of n is your primary.
Yeah, just a second. So our general equation was this, right? This is our primary equation. The starting equation is T of n equal to C of n plus 2Tn by 2. This is our starting recurrence relation. Now I want to do back substitution, in which where I am doing back substitution, I am doing the back substitution in the recursive part. Because in these constant parts, we do not do any back substitution. We only do back substitution for the recursive part. So this is my recursive part, 2Tn by 2, this one. So I have to do back substitution over here. So that's why I need to find the value of Tn by 2. This value I need to find if I have to substitute it with in the back. So that's why I'm trying to find Tn by 2 over here. That's why we wrote Tn by 2, substitute this in 1. And I found the value of Tn by 2 equal to this. Right? How I am doing? By doing n, replacing n by half, n by 2. Because I need to find n by 2. That's how we did that. And then I'm putting the value over here. But here, what is the recursive part? Here, the recursive part is this one.
Yeah.
Correct? So here, the recursive part was Tn by 2. That's why we found the value of Tn by 2. That's why we found the value of Tn by 2. this is the value of Tn by 2, and then I put it, then I did the back substitution. But here the recursive part is T of n by 2 square, right? So if I have to do back substitution, I have to find what? I have to find the value of Tn by 2 square.
Yeah.
Okay, okay. So then have to find the value of Tn by 2 square. So how can I, that's why we wrote over here, reapply that substitution. So how can I find, how will I get the value of Tn by 2 square now? That's the question. If you reapply the substitution once, then only you will get the value of, I mean, Tn by 2 you got, and then apply you got there n by 2. Then only you will get Tn by 2 square.
Mhm.
Right? So here I got Tn by 2. So what was Tn by 2? It was Cn by 2 plus 2T by 2 square. Right?
Yeah.
Now if I have to find the value of Tn by 2 square itself, right? So again, here I would, this is my equation, 2 suppose. So now this would become n by 2 square, and n equal to n by 2 we wrote, so C n by 2 square plus 2
n by 2 cube.
yeah. Fine.
Yes.
So this is my value of Tn by 2 square. So now
Hmm.
I would substitute. Yeah. This is our, let's say, the second primary equal, let's name it C. So substitute in C. Now we got the value of Tn by 2 square. So this is, so back substitute it over here, which is C n by 2 square plus C n by 2 cube. Right?
Yeah.
So now if we apply it, what we will get C of n, sorry, not C of n, Cn 2
Cn.
cube
Tn by 2 cube.
plus another Cn. So basically I'm
Another Cn.
writing 3 Cn.
Hmm.
So see now, so after 2 terms, what was the general expression? This is the general expression after 2 terms.
Hmm.
Which is what? Which is 2 square T n by 2 square plus 2 Cn.
Yeah.
And this is the general expression after 3 iterations. Right? So you
Yes.
see that what's happening is if I do it for k times, it would become 2 to the power
2
k.
power k. So here, sir, the k which is unknown, we have to get the this value of k and again put it into the equation,
Correct.
right?
Yeah. And k is what? K is basically, I mean, how many times you can half it? What is k? K is basically, you're essentially, this is n by 2 to the power k we got, right? So that means
Yes.
you're dividing n by 2. How many
Hmm.
times you're dividing
K
by 2?
times.
K times you're dividing by 2. So how many times can you divide? So dividing means what? You are making it smaller. So obviously there should be some limit up to
Yes.
which you can break it. So what is that limit? When you get a single element, n gets reduced to 1. right? So
One,
I mean,
yeah.
what is n here? It is basically an array size, right? And the size of the array. So when your size of the array is 1, that you cannot break it further, right? So that means n when equal to 1 is the smallest that we can go. So therefore n
Yes.
when divided by 2, k times we are doing division, and when it is breaking it to 1, then what is the value of k? This is your equation that you need to solve,
Yeah.
right?
N
And
by 2.
yeah, you take 2k over here, multiply it, and simply put log, you would get it equal to log n
Log n.
equal to k.
Hmm.
Substitute that over here,
Hmm.
and then you get this answer. So this n log n is your equation. Time complexity, sorry. Fine. So again,
This is from Mozart, right?
yeah, this is Mozart. That's why complexity of Mozart is n log. Okay, so this is how you solve recurrence code, and simply again for, if we take another simple small example for a recurrence, let's say t of n equal to t of n minus 1 plus say constant time. So this is t of n minus 1 plus constant means c, right? So after this, what we would do? This is our term. So I need t of n minus 1 in order to do back substitution, because t n minus 1 is the recursive part. So what would be t of n minus 1? T of n minus 1 is what? Simply substituting. Substitute n equal to n minus 1 in 1. This is 1. Right? So all you have to do while solving recurrence is, there would be two parts. Any recurrence. First would be the recursive part, second would be the non-recursive part. Right? So you need to figure out which is the recursive part and what is the parameter over here. So in the recursive part here, the parameter is n minus 1. So all you need to do in the next step is find the that recursive parts. Just substitute whatever is there in the recursive part in the primary equation, like in this main equation, in order to get this. So here the recursive part has n minus 1 as the parameter. Therefore, I am substituting n equal to n minus 1 in 1, the primary equation. So what will I get? T of n minus 1, the substitute over here. So n is n minus 1. So this thing would become T of n is n minus 1 minus 1 plus order of 1, basically C. C. So what is
So
this?
can we write it as n minus 2?
Yeah. I'm just writing so that it becomes relatable.
Yeah. Sure.
So T of n minus 2 plus C. So this is my next term. What would be the, plus here just a second. Substituting n equal to n minus 1, okay. T of n minus 1, T of n minus 1, fine. So T of n minus 2 plus C. So this is what we got, but this is equal to T of n minus 1. Right? So this is basically equal to T of n minus 1. Right? So now I got T of n minus 1. So all I need to do is substitute it back in this place. Right? So again do the T of n equal to T of n minus 1, I would substitute with this T of n minus 2 plus C plus this C. Let's say this is C1, let's say this is C2. C1, C2. Got it? So this is what I get after one level. Again, if I repeat it, now what is, this is my new equation. Right? In this equation, if I again have to do back substitution, what do I, same formula. All I have to do is now find what is the parameter in the recursive part and find the value of that recursive part in its primary equation. So here the parameter is T of n minus 2. So all I need to do is find T of n minus 2 by substituting n equal to n minus 2 in our in the previous form, right? So that's why we got here T of n minus 3 plus constant, right? So simply substitute that again over here.
For which
This would
sort
be,
we are getting this complexity, sir?
sorry,
For which sort? Or which, or it is
this is not
general?
any sort. I'm just doing a random example.
Okay. Random,
C3,
right?
yeah, C2 plus C1. So basically, you see, after 3 iterations, I'm writing this C1, C2, C3 just so as to indicate, I mean, at which level I'm getting which constant. But these are all, numerically, they are all same value. Okay, C1, C2, C3 are same value. So I wrote 1, 2, 3 just to indicate that at which level of iteration you are getting 1 and 2 C1 and which level you are getting C2. That's right. But C1, C2, C3 are actually same. So after 3 iteration, my general form is this. So sorry, my form is this. So basically after k iteration, what I would get? P of n minus k plus k times c. Right. So this is what 3 times some constant c. So here it would be k times c. Fine. So T of n is equal to T of n minus k plus kc is our general term. Now again n minus k would reduce to 1, or you can consider when n is equal to k, right? Then it reduces to 0. That is n minus k. So initially we were dividing. So division can go up to a unit up to 1, right? A single 1 unit element. But I'm now subtracting. So for subtraction and addition, the unitary element is 0, right? Because you can subtract even one cell is there, I can just remove that one cell, right? So what I mean is, so let's say you have a array of one cell. Only one cell is there inside the array. Okay. But if you want to recursively apply this code again on that one cell by dividing it into half, that you cannot do because a single cell cannot be divided into half. It would be 0.5. That's not possible. But certainly, if you have one cell, you can apply subtraction on that because 1 minus 1 would be 0. So that would be your applying something on that last cell. That's it. But you cannot apply something on half. So when you are doing division and multiplication, the element would be 1 till which you can grow or reduce. Sorry, till which you can decompose. But when you are doing subtraction, then the element that you can go up to is 0. So n minus k is basically 0. Or n is equal to k. So in the initial base case, what did we do? N equal to 2 to the power k equal to 1. So this was our previous base case, right? This is our current base case. So
How it is zero?
So, sir, how to decide this base case? I mean,
Yeah,
if
you
it's
have a
not
single array. Just intuition. So you have a single array whose size is n, right? Can you divide a single
no.
cell of
When
an
we will
array?
decide? When we will decide it is 0 or 1?
When will you get? If you do multiplication or division, what is the identity element? I mean,
1.
identity 1, right? So that's it. If you are doing division, your identity element is 1. You are dividing n by 2 to the power k. That means you are doing division. You can divide an array up to a single cell. You cannot go for 0.5, right? But you can certainly, if you are subtracting, then you can certainly go till a 0 cell array because, I mean, one last cell is there. You are applying your algorithm one more on that cell. That's it. The last cell is also exhausted. It becomes 0. That's the last iteration. So when you are doing subtraction, anytime this parameter is in the form of subtraction, that means you can go up to 0. Because subtracting can go from 0, can reach till 0. Subtraction will never reach to 0.5, 0.6, 0.7. Because this is an integer subtracted from an integer. So any integer subtraction would fetch an integer. But when you are dividing, then it shouldn't be coming in fraction. That's why we are going till 1. Right? So when you are doing subtraction, it would be n minus k equal to 0. When you are doing this division, it would be n by whatever it is, 2 to the power k, 3 to the power k, whatever, anything, whatever, equal to 1. Fine. So n minus k equal to 0 or n equal to k is your base case. So this is your base case.
The subtraction you are concerned with while we are doing the recursive call. Doing the recursive or you are doing subtraction, then it will be considered like that, no?
Yeah.
Okay. Right.
So n is equal to k we got. I mean k is equal to n we got. So therefore, what would this look like? This would become constant because this would become t of 0, that is at the last level. So this is basically a constant. Here t of 1 would be constant. Here t of 0 would be constant. And the last iteration, the base case. So this is how much time does the base case take? The base case in recursive code is basically the if case, right? That takes a constant. If executing if statement is a constant time. So that's why these two are constant time, both of these. This is a constant time work. I'm not writing it. So this is C plus K is now what? N, we know, right? So NC. So now we consider asymptotically the higher term, which is NC, which is equal to order of N. Fine. So order of N time is required to do this. Fine. So by the way, this is actually, if you write the factorial code, then the recurrence relation would be like this. Because how would the factorial code look like? Factorial some number n, right? Then you do the let's say if n is equal to 1. Let's go up to 0. N is equal to 0. Then you
Return.
1
Sorry.
is return factorial n minus 1 to n. Fine. So that's it. Now, if I have to find the recurrence relation of this, what would it look like? Two parts. T of n equal to what? Two part would be, any recurrence would have two part. I am again repeating. Recursive
First
part,
is the base
non-recursive
case.
part. Okay, so yeah, so just tell me in form of the recursive part and non-recursive part. What is the time complexity of the recursive part over here?
T
T
of
of n minus 1.
n minus 1.
T of n minus 1. That's it. And what is the non-recursive part?
T of 0.
Order of 1.
Order of 1. So that is T of n minus 1. We are removing order, so put a constant. Right. So that's why we reduce this time complexity to order of n. So that means the factorial. What is the time taken by executing factorial in a recursive manner? It is order of n. Okay.
Yes.
Fine. One little thing, although it might not come in the examination, but still I'm asking. So let's say you get this kind of the example that I had in the previous slide, plus let's say n square. Now, how will you solve it? Because there would be two this will go, back substitution will happen in T of n minus 1. Here also you will have back substitution. Till now, whatever we have solved, it had only one recursive part. Like this one we had, like in that case we had 2Tn by 2, but only one of them was the recursive part. Here I have two recursive parts, right? So how can you do it? See, since anyway we are analyzing asymptotic complexity, so we would consider which term. At the end of the day, we would consider the larger term. So like here, while solving, we got these two terms. Two terms we got. We considered this term because this is the larger one, and we ignored this one. Like in the merge sort example, we actually, if you remember, we got two terms. The first term was n log n, and another term was n. And then we say that it was order of n log n. So we remove this n part, right? So we always consider the higher term in asymptotic complexity. So whenever you get multiple like this, let's say not it has given more than two terms. Let's say I give you 4 or 5 terms, right? So how can you analyze it? Is simply think that which one would grow larger. Which one will continue longer. Yeah. So which one will continue longer? Longer means which one will have more recursive call to the base case, right? Both of these would grow. It is reducing n by 1, and here it is reducing n by 2. So which one will have more recursive call till the base case?
N minus 1.
N minus 1, because it is subtracting by 1. So in order to reach 0, it would take more time.
More
And
time.
so that means more recursion would happen for T of N minus 1. So that there would be more number of recursive calls for T of N minus 1 part. So basically, if you do the back substitution, how this would look like, right? If you do it in the form of a tree, so the left nodes are
So,
your N
sir,
minus 1,
we have
right
N
nodes are,
minus 2.
yeah,
Sorry,
I'm telling.
sir, N minus, okay, sorry.
Yeah, I'm telling. So left nodes are N minus 1 part and right nodes are N minus 2 part. Again, from here you do left and right. Again, from here you do left and right, something like this. So there would be some point coming where your only left node would continue like this and the right node would halt because your N minus 2 has already reached the base part. If you still not get this thing, it's fine because we have not discussed tree and all. In Python, did you all learn recursive tree? Was it taught to you?
No.
Okay, no problem. Let's
No,
just
sir. No, sir.
fine, no problem. Just assume as of now that within these two terms, the one which will have more recursive call, that is obviously T of N minus 1. So you consider only T of N minus 1. Just write T of N minus 1 plus N square. And now you solve it.
So, sir, this type of example are possible?
Most probably it
mean-
wouldn't come, but I mean, in our examination, it wouldn't come most probably. Maybe in the end term, it might come. Okay. Again, let's say if I tell you another example, T of N minus 3 plus 2T N by 3 plus T N by 2 plus T 7N by 9. Now, what do you think? Which one should you consider? Plus, let's say, some order of N cube. Or let's say, make it a little more difficult. C into N log N.
So, sir, from these many functions, we have to check which is taking longer time to reach the base case
Exactly.
out of all
Yeah.
these.
So out of all these 4 terms, you need to just see which one would take more time. So see, within N by 2 and N by 3, you can obviously see. And
N by 3 will be
N by 3 is dividing it by more, right? So if it is dividing it by more, then it would, so let's say 10. So how many iterations would be taken by, when let's say put N equal to 30. So from how many times it would iterate?
10.
10 times? Are you correct? So when it's 30, you divide by 3, you get 10. So this is my iteration 1. So this is iteration 1. Then you divide 10 by 3, which is what?
3.
3. This is my iteration 2.
Hmm.
And 3 by 3,
1.
which is 1. This is my iteration 3. So 3 times. 1 means base case, right?
Yes.
Base case. So basically you are running till 3 times.
Yes.
So when N by 3, this would N equal to 30, it is running till 3 times. Let us see for
N by 2.
10 by 2. So 30 by 2, it's 15. 1 iteration. 15 by 2, 7. Second iteration. 7 by 2, 3.
3.
Third iteration. 3 by 2, 1. Fourth iteration. So obviously N by 2 is iterating more.
Okay.
Now, it is quite intuitive. I just gave you this example. The thing is, when you're dividing by a larger number, it is obviously getting to the base case faster. When you're dividing by a smaller number, then obviously it would take more time because you're dividing by smaller, right? So it would take more time. So 2t n by 2 obviously defeats n by 3. So remove this whole thing.
Yes.
Right. Okay. Now your competition between 7 n by 9. So whenever you see this kind of example, so whenever see this kind of example, right, T of sum A n by B in this format it is there. Always try to convert it into the format of T of, you have n, right, by some alpha. right? So how can you write it? I mean, because a by b, do this a by b and solve it. So what? How does it look like?
7
mean,
by
by
9,
b by
sir.
Yeah, 7 by 9. So how can I write it in the form of this?
n by 9 by 7. N by 9 by 7.
Exactly. N by 9 by 7. So you
Sorry,
do
sir, I didn't get this.
this is normal arithmetic. So if you
Okay.
have 7n by 9, so anything. So this is the format basically. Let me write. I did not write it over here. It is actually like this. N by, let's say this is right. So b by a. Okay, a n by b means n by b by a. So here I had 7n by 9. I can write it as n by 9 by 7. Now what is 9 by 7? 1 point something, right?
Yeah.
So this is so 9 by 7 means what? T of n by 1.7892, right? So 23 but
1.23.
2s are 14, 6, right? 1.2. Let's keep it as it. Some terms will be. It is 1.2 something.
It will
7
take
n by
more
9.
time. No?
Sorry.
It will take more time because the denominator is lesser than 2, so it will take more time, right?
Yeah. I'm not
Can we
coming. I'm
decide?
not yet come. So I'm coming to that.
Okay.
So
Okay.
T of n by 1.2. So I'm just removing this and writing it as T of n by 1.2. Right? So now I have these three terms in which I have to compare. Right? So compare between these two, which one would take more time? I mean, more iterations, more recursions. Sorry.
T of n by 1.2 will take more
This
time.
one, because I'm dividing by a smaller value. So smaller
Yeah.
value will take more time. So obviously I can erase this one.
Okay.
Now I have two terms, T of this n minus 3 and T of n by 1.2. Now you have to think which one would take more time. So this is where you have to do a little bit of analysis to think about it a little bit, how you can do it. Which one would take more time? So basically when I'm dividing.
Sir, subtraction. Sir,
N
Yeah.
by 3.
sir,
N
the
by
one
3
with
will take more
subtraction.
time.
Sorry, can you repeat?
The n minus 3 will take
minus
more
3
time.
will take more time.
N minus 3 would take more time. How many times would take? So let's say I'm doing every time I'm subtracting by 3.
30. Let us take 30. 30.
N minus 3, sorry. If I'm subtracting an element by 3 every time, how many times would it go till in order to reach 0?
10. 10 times.
Not 10 times. Consider
No,
it
no.
in general terms you take.
3 times. No, sir. 3 times because n will be k.
N would be k.
No.
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 What is the question, sir? What is
Just a minute, just a second. Okay, so where was I? Yeah, T of n minus 3. So when I'm subtracting n by 3 every time, how many times would I need to do that in order to reach 0? I mean, how many times I need to do? So n minus 3k is equal to 0. This is what I mean. So that means
by 3 times.
n equal to 3k
3k.
or n by 3 equal to k.
N
Simple
by
thing
3.
now. What is the meaning of subtraction? Multiple subtraction. Multiple subtraction means division. Multiple addition
Yeah.
means multiplication. Right? So n by 3, k is n by 3. So basically n by 3 steps is required in order to reduce it. Right? So this would take n by 3 steps.
3.
Done. So now let's analyze the other one. What is this? N by 1.2.
Hmm.
So how many times would it take to reach n by 1.2 if I do it k times in order to reach 1? Right? So what is the same thing if I do n equal to, sorry, 1.2 to the power k log n, let's say base 1.2 equal to
Log n.
k log 1.2, 1.2, which cancels out, or I get k equal to
Log n.
log n base 1.2. So this would take log n steps. Now, which one is more? Log n is more or n by 3 is more?
Log n.
Log n,
So n by 3
By-
should be.
which one is greater value?
So n by 3 should be greater.
N by 3 is greater, obviously n by 3. Put values, obviously log means it's a smaller entity. So
How,
put
sir?
any value. Any times if you are considering logarithm is always a decreasing. I mean, not decreasing in that sense. It is much slowly growing. Its steep is much lesser, and polynomials are much fastly growing, right? So anyway, so what is the if I ask you that which one is larger, order of n or order of log n? What would be your answer? Order of n. Which one is larger?
Larger. Okay.
Order of
Order
n.
of,
And
that's
then
the
n.
thing. So this is just functional analysis. Anything which is polynomial, it's when the value of n becomes large, obviously that will grow much faster than the logarithmic value. So Tn by 3 would take more number of steps than your logarithm.
Excuse me,
Right?
sir.
Yeah.
If we can directly find slopes and compare it,
Sorry?
we can directly find slopes for them.
Slopes.
Yes.
What do we, how is slopes relevant here?
Then we can find how it is growing.
Oh, you need to find how it is growing. That thing I already discussed, right? Limit n tends to infinity, that thing. Basically, there also you are finding slopes, but what is the meaning of slope? Tell me this. How do you find slope?
By different
Sorry, repeat.
by differentiating it.
By differentiating, exactly. So the formal way of doing that is simply put your function 1 on top and function 2 on bottom, and then apply this limit n tends to infinity when your that is your input size is very large. What is the behavior of a function 1 by function 2? And do the, obviously most probably it would, both of them would come in infinity by infinity form, because here one term of n would be there, here also one term of n would be there. So in this example, limit tends to infinity log n by 3, right? So this is our term. So if I apply it over here, both of them are infinity by infinity form, so I can apply L'Hopital's rule. Infinity by infinity form, I differentiate, right? So you just apply that rule, I get limit n tends to infinity, log n's differentiation is 1 by n by 3's differentiation is what? 1 by 3, right?
It will
So
come to 0.
yeah, so this
Zero.
would become 3 by n, and limit n tends to infinity. So this is basically anything by infinity is 0. So I get this 0. So once you get 0, so that means your denominator was faster. I mean, it grows at a higher rate. Otherwise, you would got infinity, right? If you get 0, then your denominator is growing at a steeper rate. If you would have got infinity, then your numerator would have been growing at a higher rate. So here I got 0. That means my denominator would be growing at a higher rate. What is the denominator? N by 3. So n by 3 is larger function. That's it. The same idea. So that's why n by 3 would take more steps to actually reach to the end. It's larger, and that's why n by 3 is n by 3 is the term that we should consider.
It means
So,
F2,
sir,
function 2 is the larger function, right? So
Yeah.
fastest growing function, right?
Yeah.
so sir, larger the function means order of that function will be taken,
Order
right?
is more. Order is more. Basically, it means I mean, which one is growing at a steeper rate. That's that thing. That's it. Right. So that's something else. But whatever I discussed in this example, that is basically which one is taking more number of steps. So n by 3 is obviously larger. Just put values, right? If you want to check over here, you can just put values and check that. Like here I did with these examples, right? These examples. We can just do that. Check values that n by 3, it would take more time to reach the end. But log n would very fast, it would move away. So basically that's how you eliminate all of these terms and you end up like the last one term, and this is your recurrence basically now. Right? Plus Cn log n, and then you solve it. This is your recurrence. But this is asymptotically fine, and that is the most, I mean,
Okay.
even these kind of sums wouldn't be coming in your examination. Most probably in n term, it might come or it might not come, but just keep this thing in mind. But once you know this, I think any kind of recurrence you can solve. I mean, you just have to think which one I would pick and then do the back substitution as I discussed just before. Fine. Okay.
Yes, sir. It was very good session, sir. Means very good explanation, sir. Got much insights.
Hello,
Thank you
sir.
so much, sir.
So,
Yeah, any other doubts?
Sir, in this, can you explain any trickier example to kind of find the complexity for like code? I mean, can you take a trickier code to to find its complexity in one example? So,
I discussed the recurrence code, right? So if you want some
time
non-recurrence part, yeah, time complexity only you are doing.
yes, sir.
Yeah, all the recurrence part is time complexity. If you want
But
some
of
non,
some,
okay.
sure.
So okay. Let's say. Okay, fine. Fine. What is the complexity of this code?
So this code will run infinitely because zero in yeah. Because
Yeah. Oh, sorry.
J0, right? J equal to 1.
Yeah. Okay, now you tell me.
so n square log n.
Sure.
Sir, n log n. No, sorry,
N
sir,
square log
sir,
n.
let me. So I said
So-
there are 3 loops. Okay, wait.
Think about it. If I add another while loop over here, let's say
Sir, n square log n.
fine. Let us add something more. Not J. Let's set a constant n. If I write n minus 1, then what would be the case? If I write m minus 2, what would be the case? If I write m by 2, what would be the case? Oh, and by the way, here I must update.
Sir, this while loop and the inner for loop are both inside the while loop, na?
Both inside the while loop, and here I am updating this j is equal to j into 3. That remains same.
Okay.
Now here.
Sir, if it is m minus 1 or m minus 2, then that log will be removed. But if it is m by 2, then it will remain same, that n square log n.
Take some time, think about it. Are you sure? Fine, so let's do it in this way. So
Yes.
how much time does this take?
So
Order of n.
Order of n. How much time does this take? Let's take the first one, that is n equal to m minus 1 case. Take that. How much time will this take?
the m.
M.
So
Order of
n, sir. Actually, m is equal to n, right? Yeah.
order of n, because I'm subtracting by 1
Yeah.
and we are initializing here with n.
M equal to n. So that's why you have written n. So
Exactly. So this is order. So basically, inside this loop, I have these two tasks. And this is basically order of n plus n. right?
Hmm.
Fine. Okay, done. And then I have to find out what is happening in the while loop.
And this is option, sir. M by 2 and M divided by 2, M minus 2 and M by 2.
Yeah, n by m minus 2, m by 2 I have not yet discussed. As of now, we are discussing m minus 1 only.
Okay,
That's why
okay.
it is
Three options are there.
order of
Yeah, yeah.
3 options are there. In case 1 I am discussing. So this is order n, this is order n, both of them are order n. And while loop, the overall outside while loop, right? So this is order of n plus n. The outside while loop is, what is the time for that? How many times will it go?
So log n.
Log n.
Log n, because I am multiplying by 3, right? So if I am doing multiplication by 3, so how much time would it need in order to reach n? So that basically means if I am multiplying a number by k times, I'm multiplying, right? C to the power k. K times I'm doing the multiplication. So how many times can it, I mean, it would need to reach n, right? So that essentially, if you apply log, it would be k log 3 log n. And let's say we applied base doesn't matter, so I can cancel this log by assuming it to be log 3. So my k is basically log n. That's why this is log n. So log n is the while loop. So while loop is iterating log n times, and inside the while loop I have 2 other for and another while loop which are iterating order and order n. So the whole thing turns out to be what? Log n into n plus this my whole thing. And now I have to think about the outside for loop, because I have till now I have reached to this point. Next thing I have to think about is the whole for loop. Right? So how many times is that going? It is inside the range function of n, so that is happening n times.
Order of n.
N times. So that is order of n. So the total multiplication term will I am getting is order of n times
N times log n.
Yeah.
Okay, times. Okay.
Same thing. Doesn't matter. Commutative multiplication is commutative, so anyway you can write it.
Okay.
So this is
N square
n
plus
square. 2n square actually.
2n square.
Log n. Now when I am applying asymptotic notation, the 2 goes away.
N square log n. Nice.
Fine.
So, sir, here as you did it step by step, so if some complex problem come, then we have to do it like this, right?
If any complex problem comes, always start from the innermost part. See, from where I started, just I went to the innermost part. So what is the innermost part here? This scope, right? Now in this scope, I have 2 loops. That is fine. That's not a problem. But I do not have anything inside this for loop, right? This green scope, this one is the last scope that I have.
Yeah.
So inside this I have 1 for and 1 while. Let's say if I had another, let's say something was there inside it. So let's say here I had some while loop. Something is there. So then you have to at first go for this part.
2 whiles.
Right. So just think what is the innermost part and find the complexity of that. So in our example, it's not here. So let's say in our example, these 2 are the innermost part. So find the complexity of that order n, and this is order n.
Sir, there are 2 different loops, like in the inside inner loop, for and while. So you did a plus addition of both the
that means plus. Exactly. Right? That means
plus
because
is just because both are at the same level, na?
Both are in the same level.
Same level, huh?
Both are
different also loops, I think.
Right? So whenever the scope changes, so both of
while inside the for loop, then
yeah, correct. So both of them are in the same scope. This for loop and this while loop are in the same scope. That's why I am doing addition, n plus n. Right?
Yes.
This is n, this is n, and you do the addition order of n plus n. When I am going out of the scope, right? So which is the outer scope? Outer scope is this while loop. So for every iteration of this outer while loop, every iteration of this while loop, both of these loops would run. Both of these loops would run for every iteration, every singular iteration of this while loop. So that means what? For every singular iteration, if both of these loops run all the time, that means I have to do multiplication. So whenever the scope changes, that's when you do multiplication. But within these two loops, I'm not changing the scope. These two loops, the scope remains same. So that's why addition. So n plus n, and then I am taking this whole time is taken log n time, but this is outer scope. This for outer value. That's why I'm doing this multiplication with the inner ones, right? Whatever is inside that value, which is n plus n. Again, I am going one more scope outside for this for loop. That's why again I'm doing this whole thing under multiplication over here. This multiplication. Right? So whenever the scope is outer scope, you do multiplication of all the inner elements that it has. And whenever you are within a particular given scope and there are multiple loops that are inside it, you do addition of all the types. Fine.
So, sir, anytime such complex function come, we have to go first to the inner loop, and then we have to come out from these inner loops to outer loops.
Exactly.
Okay. So we
So
kind of
it
multiply.
It is kind of the bottom
Right?
bottom approach.
Bottom up approach. Exactly.
And so, like as you asked, like if we change the value of m minus 1 to m by 2, then also it will remain same, right? N square log n.
If I change m from m by 2, if I do,
Yeah, so
then
then
what will
also
happen?
it will remain same. It will remain same n square by log n, because on that for loop is bigger than like log n, so it will take log n on only, and that's why it will remain same n square
So,
log n.
anyway, so let us see what happens. So can you tell me what is, it may limit n square log n, but I'm not worrying about that. What are the changes that I have to make if it is n by 2?
So
What
then
will
this
change?
the while loop will become, its complexity will become log n. The
Exactly.
for loop, yeah, the for loop will remain same, that is on. But if we compare the two, then on is bigger, then we'll take on only, and then the outer while loop is log n, and the outer for loop is n, so n square log n.
Exactly. Nice. So this is log n. So this would become n plus log n. So this becomes n plus log n. So this becomes n into n plus log n into log n. So this becomes what? N square log n plus n
Log n square.
log n. Right? Now I have to consider the term which is higher. Obviously, n is larger than log n. So therefore, this term is steeper curve. So order of. Okay.
So log n square we are not taking, right? N times log n square as higher.
N times log n square is smaller than n square log n. That's why we are not taking.
Okay.
Check it. We have a nice tool, right?
N
But
square
I don't
log
want
n.
to do that. Just apply that on your own because it would take some time to apply this differentiation. Okay. Because this product rule is there. So you have to take, what is the differentiation of n square? It would be 2n. What is the
2n log n.
differentiation of log n? It is 1 by n. What is the differentiation of this term? It would be, you have to put n at first and then differentiate log n square, which would be 2 into 1 by n plus we have to now put log n square in its place and then differentiate n, which is 1. So this is your denominator. And numerator would be what? Keep n square at its place, differentiate log n, which is 1 by n, plus keep log n at its place, differentiate n square, which is 2n. Right? N. So this is what? N plus 2n log n divided by n gets cancelled, 2 plus log n square. Fine. Still it's infinity by infinity form, again differentiate, so 1 plus keep n at its place, move to out, differentiate 1 by n plus keep log n at its place, differentiate 2n, which is basically 2 Then substitute over here. 2 becomes 0 plus log n square is what? 2 log n. Oh, wait, I didn't take. Okay, fine. 2 log n. Here I didn't write log n, right? Sorry. Here 1 log n would be
log
there.
n by
In the
n.
denominator, yeah. In denominator,
2
2
log
log n.
Sorry. 2 log n. So 2 log n means 2 and log n is 1 by n plus 2 log n by n. Fine. So n gets cancelled. 2 log n divided by 1 by n plus log n. I'm not repeating, just we have to do one more time repeating. Then it would be solved. So just again apply differentiation on this, you would get infinity by, I think I'm taking which one on top, n square, right? So basically you will get infinity as the answer if you apply one more step of differentiation over here. So fine, just apply this differentiation one more time, you would get infinity as the answer, which means basically n square log n is a larger term.
Okay, sir.
So don't, I mean, just for formally you can see it like this, but if you have to just apply, simply see what are the terms. N square log n is 1, another is n into
N
log
log
n
n.
square. Right, now all you have to see 1 n is common, so remove this. So what are the terms that we have? 1 log n is common, so remove this 1 log n. So you have in this term 1 log n is there, and in this term 1 n is there. So which one is larger? N is larger or log n is larger? N is larger, right? So that means this whole term is larger. Simply like that you can logic. For difficult function, this way of checking is best. Okay, let me just discuss one more example over here.
Sir, one question.
Yeah.
Hello, am I audible?
Yeah.
Am I
Yeah,
audible?
you're audible.
What type?
Your voice is breaking.
Complexity.
Yeah.
Am I audible? Am I audible?
Yeah, audible, but it's breaking sometimes.
Okay. Question: how the question will be framed? The direct answers will be asked. The process of derivation will not be asked. Then, hello, am I audible?
It's breaking your voice. You are asking how questions would be framed for complexity. The question of one code would be given and 4 options would be given to you. Which one is the correct complexity for this code? Okay.
It will be given.
Just to see.
Hello.
Yeah.
So I'm discussing another problem.
Yeah.
Okay.
And what is the time complexity of this code?
And login.
Yes, sir. N log n.
Sure.
Yes, sir. N log n.
Yes, sir. Sure.
What is inside the while loop?
Yeah. And log n.
So won't it be log 1 plus log 2 plus log 3 up to?
Take time. Yeah, correct. Actually correct. But for others also, let everyone think. So it's not n log n. It's something else. See what it comes down to. This is not n. This is I. Now think. This is I. Now you
What
think.
are you printing, sir? Printing J?
Doesn't matter. J plus 1, whatever. Basically, I'm just doing order one task. That's what I think. Print 100.
Okay.
N square log n.
What is the time of the while loop?
Sir, actually, sir, even in the, I think in the end, it will eventually be.
At the end, I'm not talking about. I also don't know what would happen at the end. Just tell me what is the complexity of while loop over here. One iteration of the while loop, what time it could take? One single iteration of the while loop.
Log of I?
Log of I, correct. So the
Log I,
not
yeah.
one. Yeah. So since initially we had j less than equal to n, that's why the time there was log n, because
Log
you
n.
are you are reaching j, you are reaching n inside the previous example. Starting j equal to 1, reaching j equal to n by multiplying j by 2. But here I have I. So that means what? It's not log n, it's log of I. So you are reaching till I. So this code is order of log of I.
I.
Right? It's not n. And how many times am I doing that? It's inside the outer loop, right?
N
So
times.
for, yeah, so n times we are
N log
doing
I.
n log I, but you have to think about that. So initially when I is, let's say, 0, right? So then how many times the while loop would run? When I is 0, let's say I is 0, I is 1, I is 2.
One time it will.
3, 4, 5. Right? Let's say like we take example till 8,
Yes, yes.
and then let's say dot 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 up to n. So when I are these values, then what would be the, how many times my j would run? So
N
let's
by
say
2.
One
N by
time.
2 times. N by 2 times.
while loop runs. How many times?
N by 2 times.
No,
Is
one.
it correct?
No, only one.
So while j is what? J is 1,
J is
and when
1 and
1 is less than equal to
0.
0.
Hmm.
It's not correct, right?
Oh,
So
okay.
it would not execute. So
Okay.
while loop would not complete its execution, so that's fine, no
Okay.
problem.
Sorry.
When I have I is 1, so then what would happen? Yeah, one time while loop would execute.
Yeah, one time.
Okay. So after that, when it's 2, right? I is 2. So how many times will it execute? You already saw that log of I. So log of 2.
5. Okay.
Log of 2.
What
Log
is
of 2.
log of 3? Log of 4. Log of 5 times dot 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 log of 8 n times. Not n minus 1 actually, because yeah. So from 1 to n minus 1, these are the iterations of the while loop. While in the previous case we were writing n into log n, because when I was actually 0, 1, 2, 3, 4 dot 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 up to n, j was actually running how many times? For 0, it was not running. Let's say it's not going, and then for 1, it was running how many times? It was running n times, right? Anyway, it was n times because we had j less than. This is the case where while j less than equal to n was the example, right? So when I was 1, then also j was running n times only because the while loop was with n, so n times. When I was 2, then also while loop was n times only, therefore it is still n. When I was 3, then also n times. So every time, whatever be the value of I, j was running n times because the inner while loop condition was j less than equal to n. So it doesn't consider what is the value of I, right? So every time it was running, j was running n times. So that's why the total number of iteration was what? N times I'm doing for all the n I. So therefore, n into n.
And
Right.
square.
So like that. If I assume it like that, and okay, so I made one mistake. Here I'm assuming j was being increased by 1, j equal to j plus 1, suppose. And but in my example, I told you it was j in the previous example that we took. There j was not plus 1. There j was j by 2, suppose. J less than equal to n, right? So j into 2. So that means here it was log n times. Right? So j into 2. Same thing. Initially with n times it would have run if I would have used j plus 1. Then it would be n times. Since I'm using into 2, it would be log n. But the point is, whichever you take, here the condition was with n, not with I. Therefore, outside loop, whenever i's value is whatever, I don't need to think about that. Since the inner while loop is running n times, inner while loop's condition is with only the n variable. That's why every time it would be log n or n. I mean, depending upon your update is j into 2 or j plus 1, it would be either log n or it would be n. But it has nothing to do with I. So every time it is, let's say, if I'm considering the j into 2 as the update statement, so log n is the number of iterations, and I have n such outer loop. For every I value, I am doing log n time. Therefore, it is n times log n. That's why we got n log n. Right, and we had another outer loop which was creating the n square error.
Whether it is j is equal to j into 2 or j by 2, the time will be log n.
Yeah, suppose this is not there. J into 2 I'm talking about. Right? So what I mean is every time it was using this n variable only. But in my example over here, I have now used the I as the variable in this place, not n. So that means here I was getting log n, log n, log n because n was the variable over here. Here I have I as the variable, therefore what would I get? I would get log 2, log 3, log 4, log 5, like that, accordingly.
Sir, but when we are using I equal to 2, so
yeah,
here j is 2, so 2 is equal to 2.
sorry?
I'm saying, sir, you have taken 2 and while loop is running log 2 times.
Yeah.
Yeah.
So see, basically what happens is, since here I'm doing j into 2, right? So that means actually if you have to calculate, you have to consider the base as 2 in all of these cases. So if I take this example when I is equal to 2, right?
Yes.
So since here I'm considering asymptotically log I, right? So therefore we have to consider it for larger amount of spaces. So if you take log base 2, then you would get different one or two values would differ. So here I put log 2 base 2, it would be 1. Right? It would be 1. So when when I is equal to 2, if I check over here, j equal to 1 with j equal to 1 I'm starting, right? So first 1 is obviously less than 2, so that means one time I'm executing. And then what I'm doing is I into 2 I am doing. So, sorry, 1 into 2 I am doing, so it becomes j equal to 2. And then also it is satisfying, so it is going for 2 times. So this is happening because of one boundary case of this equal. It doesn't matter because at the end of the day it would be plus 1 plus 1 plus 1 would be reduced, so that doesn't affect. Even if you do it, even if you remove this equal to part, then also it is okay. Right? That because asymptotically it doesn't matter. You don't have to count the exact number of iterations. Anything it is increasing j equal to j into 2 and it is up to j less than I, that means it is log I. If it is j less than n, then it would be log n. Because your update statement is into, right? That's right. If your update statement is not into, it is addition, j plus 1 or j plus 2, then it is order n. If it is into, then it is log n. That's what you have to keep in mind. Okay. This
So-
base things change a little bit. If I remove this equal to, then it would be exactly same. So now you see j is less than I, so now it would iterate only one. Okay. So actually, if you have to exactly find the arithmetic part, then it should be the ceiling value of all of this. Fine. But don't get into so much difficult, I mean, so much analytical
confusing.
part. Yeah. So that's what I'm saying. Don't get into the ceiling values. So that's what I did not write it in the first place. So just have this analogy in mind that if I am writing update statement as j into 2, right? So that means into 2 into 3, whatever. When I'm having into as the update statement, that means my complexity of the loop would be logarithmic times. Now, what would be the log? What would be the log factor? The factor would be whatever is there inside the while loop, j less than whatever, j less than n, j less than whatever it is there. Log of that would be your answer. So
Yeah, here it is I, sir, and j
here it
less
is
than
I.
j less than equal to I. So that's why it's
Yeah.
log I.
Log. Fine. So if that is the case, therefore, whenever I'm iterating through the I equal to 0, 1, 2, 3, 4, 5, 6, it would be the inner loop would run, while loop would run. See, while loops runs for log 2, log 3, log 4, log 5, right? Because log I is the case. So therefore, the total time, the total number of iteration is what? When I is 3, inner loop runs log 3 times. When I is 4, inner loop times log 4 times. When I is n minus 1, inner loop times log n minus 1. So the total number of iteration is log 1 plus log 2. Now one of you already said that in the starting. For others, we did the explanation. Fine. This is the total number of iteration.
Yes. Yes.
Fine. Now what is this equal to?
So we can make it like log n minus 1 factorial.
How can you just tell the intermediate step?
Because adding two logs is same as multiplying the
Correct.
multiplying them. So log 1 into 2 into 3 up to n minus 1, which will become n minus 1 factorial.
Exactly. Great. So this is how we are doing, because log of m plus log of n equal to log of m into n. And just a minute, log of m minus log of n is equal to log of m by n.
By n.
Fine. So
Yes.
these are the logarithmic. I mean, in maths, you all have done logarithms, right?
Yes,
Maths
sir.
1 or yeah. Fine.
Yes, sir. Yes, sir.
So we got this log of 1, 2, 3, 4. So this boils down to what? Log of n factorial, n minus 1 factorial, right? Log n minus 1 factorial. Any doubt?
No, sir.
Log n minus 1 factorial. So what is log n minus 1 factorial?
Log n log n. We can write n factorial is equal to n log n ki power log n.
Exactly. So when we are actually going for asymptotic analysis, right? I think I discussed that one. So you have n factorial is what? N into n minus 1, n minus 2 dot 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 up to 1. And if I write n to the power n, that is what? N into n dot 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 into n. Right? Now, if can I write the statement order of n to the power n factorial equal to order of n to the power n? Can I write this statement?
Yeah.
I can write it, because why? Because if I compare between each of these terms, then I would see
Highest order will be n to the power n.
yeah. So that means what? That every time this is similar, but for this one,
Sorry,
for this
sir,
one,
I'm not getting this.
yeah, n
N to the
factorial
power
and just see, this is the thing, right? So whenever I'm writing f of n equal to order of g of n, that means my g of n must be larger term, right?
Hmm.
That's why that is the definition of order. G of n must be a larger function. So that's why I'm writing this statement, order of n to the power n equal to n factorial. Now, how can I write this or not? So what I mean is, since n to the power n is a larger function than n factorial, that's the question. Now, yes, n to the power n is a larger function, and the reason for that is, if I write n factorial, it is equal to n into n minus 1 into n minus 2 till 1. That is the definition of factorial. And n to the power n means what? Multiplying n times. So n multiplied till n times when you reach 1. Right. Now, if I compare between these two functions, n to the power n and n factorial, I see that the factorial term here it is n minus 1, but n to the power n has n over here. Here it is n minus 2, but here again I have n. Here it is 1, here again I have n. So that means what? N factorial is comparatively smaller than n to the power n, because each of these term of n factorial is lesser than the corresponding term of n to the power n, which is n. Here it is n minus 1. Right? So therefore, n to the power n is a larger function, and I can write this statement. It's a valid statement. So when I have log of n minus 1 factorial over here, and since I am only considering asymptotic complexity now, order of, right? Let's. If you have doubt in this, please again rewatch this part. It would be clearer.
Not clear, but I will have to.
Just rewatch. Just rewatch this part. Just a minute.
First of all, it's very confusing.
It's not confusing. It's you have to just see the factorial. Just check out the factorial definition and all. Okay. So log of n minus 1 factorial. I am now substituting with order of log of n to the power n, because anyway it's asymptotic complexity. So that is order of logarithm. We know n log n. Fine. So at the end of the day, it is coming to n log n only. That's what I told. But we don't know. But it's not exactly. If you simply say that it's because of it's a loop and you're running it for n time, it's n log n. That's not correct. Okay. You have to show how this is working.
Here's the detail.
Except the factorial part.
analysis.
How I got n minus, I mean, how we got from n minus 1 factorial to n to the power n, that's something very simple. You just check it out. The only thing that we are using over here is I can write n factorial as order of n to the power n. That's the only concept that we are talking about here.
No, my question was this.
Yeah.
This we analyze by the detail, and previously we calculated by the n log n by using total iterations. By
Sorry,
putting the values of this
I couldn't get. Can you repeat?
By putting i equal to 0, putting equal to 0 and j values of j, that was the one method, and this is what the alternative method to getting the log n, order of n log n.
It's not alternative, it's the only method. That was a separate sum. Here it's using log of I, and this is the process how it is coming. Okay, n log n is coming. This is, you don't think it in terms of that it's n log n. There are two methods.
Okay.
Only method. This is the only method. It so happens that the answer comes n log n at the end by simplifying. Okay, but if you directly say what is the exact answer, na, then I would say the exact answer is not n log n. The exact answer is actually this part only, log of n minus 1 factorial. This is the exact answer.
Yeah.
Okay, this is your correct answer. But the thing is, we can simplify this. And by simplifying, it turns out to be n log n.
This
Sir,
is for j
so-
less than I. This is j
Sorry?
less than I. Then j is less than I. Yeah, right now.
Yeah,
Okay.
correct.
And this n log n came total iteration. Previous question. This was j is less than what?
That was j is less than n.
Okay. That was for the j.
That was j is less than n. This example.
Which one?
the previous example that
Actually,
I did.
yeah.
So log n. But sir, if
Oh,
you're
oh.
taking log, sorry, j less than I, then also it's coming as n log n at the end.
At the end, because of some approximation and all, that's what we are doing, right?
And
But
you said that n to the power n is, sorry, n to the power n is,
n
oh,
to the power n,
n factorial is in order of n to the power n.
yeah.
So that we have to remember, or
See,
as you
there is a
already,
simple thing. Why it is coming n log n, you see. Here earlier it was n, right? There we directly did n log n. Right? Log n is
Yes, sir.
happening n times, therefore n into log n log n, right?
Yeah.
Here, when it was happening, when this was j less than n. But now I
Okay.
have written j less than I.
Yeah.
So here also, what I'm writing is the answer is order of n log n only. You got the final answer order of n log n only.
Yeah.
Why it is coming n log n? See, I will always be bounded by n. I cannot be greater than n in any of the iteration, right? I is 1, 2,
Yeah.
3, 4. At
Up
the
to
end,
n minus 1.
up to n minus 1. That means what? I is bounded by n every time.
Okay.
So if I am doing,
Got it, sir.
yeah, so when
Mhm.
I'm doing this approximation, right? When I'm actually using this approximation, this is actually, I mean, what should I say? Neutralizing the effect of whether I had I over here or whether I had n over here. Right? That's why this approximation is neutralizing that effect of having I over here or having n over here. But that's what I'm saying. Asymptotically, I can do that because asymptotically, I am worried about the larger function. So n log n is actually an overestimate of this code, So if I say you, so if I explain it in this manner, if the code is j less than I, fine. If the code is j less than I, in that case, the exact time complexity is order of this thing, in order of log order
n
of
minus 1
log n minus 1 factorial. This is this is proper complexity of the
answer.
code, right? But since I mean, in asymptotic complexity, I can always replace a smaller function with a larger function and put it inside O. That's why we are substituting it with order of n log.
So n log n is larger than log n
N log
minus
n is
1
larger
factor.
than log n minus 1 factorial.
Okay. And to
N
get
log n
that,
is,
we have to solve it further.
and in order to get that, you are actually using this approximation. That's why we are getting this back. Right? If you do not understand this code, what I'm trying to say is just understand this part, that what is this range of n, what is j less than I, and what is the difference between having j less than I and j less than n. Okay, understand those parts. Just understand up to this, that how it is log n minus 1 factor. If you understand up to this, that should suffice. Okay, and that's it. That's the whole. I don't think anything more than even this difficulty level wouldn't come is what I suppose. But even if it comes, nothing more than this would come in any of your analysis.
Okay, sir.
Most probably not even in gate.
Because it was I, it was very confusing. I mean, initially it was.
Yeah, that's why we discussed this, because this kind of, I mean, even if some of you are planning to give gate exam, then this kind of problems might come. I don't feel in our examination.
IITM
might
is also
help.
equal to GATE, sir.
That's fine. That is, it's not even equal. It's actually better. So in that respect, I would say,
Yes, sir.
Gate you give to get into IIT. So that's the main point. So anyways, so what I am saying is, if any one of you is trying to even for GATE exam and all, I think this kind of question might come. If you understood it correctly, whatever we discussed in today's session, you shouldn't face any difficulty in any code of time complexity in our, at least in your BSc degree, any exams. Okay, fine. Okay, any more doubts in complexity analysis or any other week 1 to 4? It's already 10. We didn't discuss anything of week 5 anyway. No problem. So we would discuss week 5 later after your thesis is over. Week 5 and week 6 is related. See, I'm just giving a brief intro.
After the quiz one, sir, because
I understood. So the thing is, let me tell one thing. Week 5, we would learn the graph algorithms, right? When we have yet, as of now, we have learned BFS, DFS. We have learned application of DFS by using pre-post numbering, and with that we learned how to remove cycles from a graph. right? Which is in your exam, by the way, week 4. So removing cycles from a graph in order to get a directed acyclic graph. Now, once I get a directed acyclic graph, then I can do the topological ordering. I think in the live coding session, topological ordering was discussed by Atul sir, right?
Week 4 live coding.
Yes, sir.
Yeah.
Yes,
So
sir.
topological ordering, I left it over there. That one topic was left, which was discussed in the live coding. So week 4 live coding, refer if you want to learn the topological ordering, it's discussed in the live coding session. All other topics of week 4 are discussed in the open session. So okay, so now we learned BFS, DFS, we learned representation of graph. We then went to application of BFS, DFS. We learned how to remove cycles and detect cycles in a directed graph using pre-post numbering and DFS by removing back edges, right? And then we got directed acyclic graph by removing the cycles, and then we learned on that directed acyclic graph we can apply topological sort, and using topological sort we can find the longest path in a directed graph, which is basically the prerequisite graph, right? Let's say which is used a lot of in real life, it's used a lot of times. Like you have this course prerequisite example, which is given in our lectures that let's say in order to do some specific course, you have to do some other 2 courses. Now, in order to do those 2 courses, you have some other prerequisites.
That
There is a chain of
topological sort,
prerequisite.
right?
Exactly. So there is a chain of prerequisite. Now, what is the minimum length of your let's say you want to finish all of those
Semester.
prerequisite and you want to complete your degree. So how many semesters would you need in order to complete your degree if the prerequisite is arranged in this manner? So that's how to answer these kind of practical question. There we learned that this is basically a DAG, directed acyclic graph, and on the DAG we could apply the longest path algorithm, right? Which is basically a little modification of topological sort. So
longest path in DAG, can you explain?
Longest path algorithm. I'm just
this has been learn it after the quiz. It is better.
Yeah. Just refer the live coding algorithm. It's there. We have discussed.
There we have discussed topological sort.
Yeah. So that's basically same. In longest path, what you do is you do topological sort. What is topological sort? Topological sort is you are removing the degree
in
zero
degree
vertices.
Vertices,
Yeah, exactly.
yeah.
Vertices every time. So that means what? Once you remove a particular vertex whose degree is 0, that means you are removing all the edges which is going out from that vertex, right? Now that essentially means all those nodes which are just after this node, which you are currently removing, right? Which is degree 0. So that node we are removing. So all the nodes which come next, the very next in the prerequisite graph, those nodes are getting reduced. Their are facing their sorry, not facing. The in degree of those nodes are getting reduced by 1 because we are removing a particular node whose in degree is 0. So what I mean is, let us do it over here. So you have this is a graph.
Topological sort only operated on the DAG, right, no, sir?
Sorry?
Only on DAG. Only on DAG.
Only on DAG.
Only on DAG.
Okay. It works only on DAG.
Okay.
That's why we learned how to make DAGs from graphs by removing back edges using
what
DFS.
works on DAG, sir?
Topological sort.
Yeah.
Okay. So you see, let's call these vertices 1, 2, 3, 4, 5, 6, 7. Okay. Tell me how to do topological sort. Which one should I remove first?
1.
Once in degree 0, so remove.
First we have to assign in degree to all vertices.
Yeah, I'm not writing all the in degrees. Just
Okay, but
See what?
for doing the topological sort, we have to.
You have to assign this. I'm doing on hand now, so we will just see and compute it. I just want to discuss how to apply the longest path concept. So at first I would remove 1, so that means 1 is being removed. See, when I'm removing 1, what does that mean? So I'm removing the node 1. That means I have to remove these 2 edges as well, right? Which are emanating from 1. So what does that mean? When I'm removing this edge, so that essentially means I'm removing one prerequisite of 2.
True.
Correct? Because prerequisite of 2 was 1, which I removed already. Accordingly, for one of the prerequisite of 7, this 7 was also 1, which I'm removing. So what does this mean? Can I do 1 and 2 together? No, right? Because 1 was prerequisite. Can I do 1 and 7 together?
No.
No. So that means
No,
1
no.
has to be done individually in the first semester. There is no other option. Correct?
Yes.
Can I do any other
Foundation.
stuff? Yeah. So this is your sem 1. Okay. Fine. How many in degree nodes do I have now which I can remove? In degree 0 nodes.
2 and 7.
2 and 7. So can I do 2 and 7 together in a single semester?
Yeah,
Yes.
we can.
Can I do any other course in the second semester other than 2 and 7?
No, no, no.
Why? Because in degree 0 courses are not there other than 2 and 7. Correct?
Yes.
Yeah, yeah.
So remove 2, remove 7. Remove the prerequisite for 3, remove the prerequisite for 6, remove the prerequisite, another prerequisite for 6, remove another prerequisite for 8. Now, what are the nodes that I can, what are the subjects that I can do now?
3,
3,
6.
6.
3 I can do, 6
Yeah.
I can do.
Yeah.
6 to 3. Remove the prerequisite for 4, remove the prerequisite for 5, and for 8.
No, 5 and 8.
5 and 8. No.
Finally, I don't have any other option, so I have to put 4 as the last.
5 semesters, minimum 5 semester is required.
Exactly. Minimum 5 stems required. Now, what was topological sort giving you?
1,
What
2,
was
7,
that?
3, 6, 5, 8, 4.
Exactly. Topological sort was giving you 1, 2, 7, 3, 6, 5, 8, 4, or 1, 7, 2,
1, 7,
3,
2,
6,
3.
3, 6,
or
5, 8.
1, 7, 2,
1, 7, 6, 3,
6, 3, 5, 8, 4.
I'm not writing all the other cases. You have to just.
A number of combinations are there.
So
Only
these
on
two,
the
yeah.
basis of the selection.
Right.
Not
So
in
this
the-
is
yeah, it is.
this is your topological sorts output.
Yes.
Fine. But this is not equal to 5.
Yeah.
I got semester 1, 2, 3, 4, 5. The result is 5 over here. So we discussed that okay, 5 semesters are needed. Topological sort gave you these different sequences, right? Any one of the sequence according to which node you are executing on topological sort. But basically, topological sort can give you any one of the sequences. That is also correct. This gives the order in which the courses should be done. First course 1 should be done, then 7, 2 should be done like that. But it is not telling you what is the minimum number of semesters needed.
Yeah.
But did I do anything different in order to get 5? Or did I simply apply topological sort? What did I do? I mean, when I was executing that node, I mean, that graph thing, did I do anything different? It was just simple topological sort, right? We didn't do anything different. Only thing is, we kept track of a particular item. And that item is what are the subjects that I can do in a particular term. That is, what are the 0 degree nodes that I have at every instant. So I kept track of all the nodes which were having 0 degree at a particular instant. So all you have to
Yes.
do in order to, this is your longest path algorithm.
Which one? This. The
This part.
sequence.
Not the sequence, this 5, this which is giving you this result.
Five semester.
Yeah, so same thing. So
Well,
what is
what-
longest path algorithm? This is total.
Why
Yeah.
this is the longest path? This is shortest path.
No, it's not shortest path.
Long.
No, it's
Not-
longest.
It's longest path. I'm telling you why it is longest path. We call it the longest
Yeah,
path because it considers all the prerequisites and then it reaches there. Right? Shortest path would be you just do not care about the prerequisite,
Prerequisite. Yeah,
directly.
directly we can do.
So that's
But
why
in
we
that
call it.
sense, yeah, it is longest path.
Yeah, in that
But
sense.
yeah. In that sense, it is longest path.
That sense it is longest path, but be very, very careful that this does not mean it is telling you the maximum number of semester. That doesn't make any sense. The maximum number of semester can be
Yeah,
infinity.
that's why I'm telling.
Exactly. The idea is from the
But
exactly.
So,
Yeah.
sir, topological sort
Got
is
it.
giving you the longest path, and this semesters, 5 semesters are giving you the and how many?
Just a second.
Sorry.
Fine. Topological sort plus keeping track of all 0 degree nodes at every level. That's what we did. That's the only difference that I'm getting over here. I kept track of all the nodes, which I can actually all the subjects in that sense, which I can do in a particular semester. That's the only only difference from topological sort that I did. I kept track of the subject. I applied topological sort. Only difference is that I kept track of the subjects that I can do at a particular instant, at a particular level. So what does that mean? In terms of the graph, I kept track of the 0 degree nodes that I have at every level. So initially I had only 1 0 degree node, then I had 2 0 degree node together, then I had again 2 0 degree node together, and then again I had 2 0 degree node together. And finally I had again the last node as the 0 degree. So I just kept track of this thing, keeping track of all 0 degree nodes, 0 in degree nodes at every level. If I can keep this track simply by applying topological sort itself, right, then I get the longest path algorithm. So I don't have to do anything else. I have to apply topological sort only. I just have to take some data structure and store this information. And that's the longest path algorithm. Now, you write the code of topological sort. I would not go to the code now. Just check out the code of topological sort. In that code, we would add one single line, just one single line, which is a level dictionary would be there. So let's say level of whatever be the node. Let's say level of I am writing
Minus
equal
1.
to not -1. So
Initially,
what is?
it's
So I'm not initializing. I'm telling the
okay.
one.
Okay.
So inside the loop, I would have level of I would be equal to maximum of either the initial whatever value was there, that, or so what is this level of j? J is just the node before, I mean the previous prerequisite of I. So that means I'm writing 3 6 over here after removing 2 and 7, right? So that means 3 6 can be done in a semester after the semester of 2 7. So what is the 2 7? 3 and 6 are, I mean, in that sense, 2 and 7 are parent node of 3 and 6, right? So 2 and 7, whatever semester we can do 2 and 7, I can do 3 and 6, that is the child node of 2 and 7, one semester after that. So that means one semester means 2 plus 1, which is 3. So that's what this is. So J. So J is my parent node. I is my child node. Okay, level of I or level of J plus 1, whichever is maximum. Take that. Why level of I am writing maximum? Why we are writing this level of I once again? The reason for that is, let's say you already had a third semester course, right? Let me just give you an example. Okay, I'm just giving you normally. So let's say you had a node over here. Let's say some Z node. So that had already been assigned a particular value initially. But again, after that, some node is there which is already traversed and it is also giving an arrow like this. So already it is higher value. So you don't have to consider the previous value. Okay. So anyways, if you are getting confused, don't need to think like this. What you can think in
It
the
is
what
just
you
like a
can think.
lateral entry. It is just like the
Yeah.
lateral entry we have made, right now.
Exactly. Exactly.
Lateral entry than the previous, not the
Yeah.
previous semester
So
will be wiped out.
So J wouldn't be child.
No.
So
J would be the node which is actually before the ith node, right? Because you're adding the level of J plus 1. That means I is level, that is current level means semester. I mean, basically, you can think
Yeah,
of that.
true.
So I can be done at a semester when J is already done plus 1. Whether that is maximum or current level of I is maximum. Whichever is maximum, I would consider that. Maximum means safe side, right? You are doing at a later part in the semester. So if you are doing later part, then that means the risk of running into a course whose prerequisite is yet not covered, that risk is lesser. Because you are calculating maximum, you are finding the maximum, which means you are doing it further in your degree. So once you are doing further in your degree, the risk of any prerequisite being left over is less. So think in that terms. Okay, so that's why it is max of level of I from a level of J plus 1 level of I. So this is basically you would add this line of code in the topological sort inside the loop where you are traveling, where you are actually running through all the nodes, right? So inside that you are just writing this line. Just check out the code of longest path and topological sort. There would be only one line of difference, and that's this line. So topological sort and longest path are basically same algorithm, only longest path you are keeping track of this information simply by applying topological sort. Topological sort plus keeping track of this information in this line of code is giving you longest path. Okay, just check that out. Should be clear. So anyways, so we learned about longest path and topological sort. That was our last thing, and we addressed this nice real life problem. And after this, now we would learn in week 5. I'm just telling the overview, which we would discuss later, not today. So week 5 is mainly about graphs, and now we would learn how to find shortest distance in a graph, which is your Dijkstra algorithm. So many of
weighted
you
graphs, right?
Yeah. So weighted graphs, and we will be learning about multiple algorithms on weighted graphs. So week 5 is about weighted graphs. And Prim's algorithm, Kruskal's algorithm, and Dijkstra algorithm, minimum spanning tree, all these things we would learn. But week 6 is again about weighted graphs. So let me tell it in this way. Week 6 is again about weighted graphs. Now, week 5 and week 6 are closely correlated. Why it is so? Because in week 5, you would learn the algorithms, I mean, on weighted graphs, this Dijkstra algorithm and all these Prim's and Kruskals and all this algorithm. In week 6, we would learn those algorithms only, but we would apply different data structure to improve them. That's the core idea of week 6. Week 5, we learn the graph algorithms. Week 6, we use a different data structure on the same graph algorithms to improve their performance. So that's why week 5 and week 6 are closely correlated, and we would be discussing them in the, I mean, this revision session would happen, and then in the week 6 session only we would discuss everything together. Right?
Okay.
And maybe we can have one more session, but we would plan that accordingly. No issues. So kind of this also kind of became a revision session only. So yeah. All the best for your exams. It's on
today
Sunday,
we
right?
discussed today we discussed time complexity and this different examples and this little bit of graph toposort.
Yeah, time complexity and this last part of graph. Maybe you all can focus on week 3, the sorting, searching part in the revision session, and BFS that coloring. Sorry, not coloring. What
2,
do I
3,
call
4.
that? Pre-post. Pre-post.
One revision session will be there, no sir? One revision.
Sorry?
Friday.
Friday would be revision session.
Okay. Okay, sir.
Okay, fine. Okay, nice.
So Friday also you
Okay,
will
sir.
take
Thank
the
you.
session, sir?
No, Friday Atul sir would take the session.
Okay.
Yeah, yeah.
Fine.
Mhm.
I would take the week 5, week 6 session for this
After
algorithms.
Sunday.
Yeah. So on Sunday you have exams from which time? What's the timing?
Afternoon, sir. 2.
After. Okay, fine. All the best.
Time has been announced.
Not announced, but usually quiz timings are in the afternoon.
Okay. Oh, thank you. Thank you, sir.
Okay,
Thank you. Good
Thank you,
night.
sir.
good night. All the best.
Good night, sir.
Thank you, sir.